I love long titles. That's pretty long. But it helps me introduce the two things that I want to share with you. The first is the idea of color that is not, that color does not exist in the point. Color exists only in the space. I will tell you what I mean by that. And there's a recent, not so recent trend. There's a quite a big trend of people that wants to transform cameras into a spectrophotometer or colorimeter, or to measure things with a camera. Or there's a big industry of wonderful instruments that measure and give you back the spectrum of each pixel, of each point in the taking a picture. But unfortunately, all this instrument and all this attempt has a big problem. And I will tell you this problem that is strongly connected with vision. So it's a circle. So we start from a point and we will end up to that point. So let's start. It's kind of well known that the idea of perceiving, having a visual perception has two components. The one is the physical components. So there's some field of light outside. This field of light is acquired, is grabbed by our eye, by our system, and so we have a perception. And this is something that has certain characteristic. And first of all, it's useless to say that our perception is very different from a camera, but we will get into deep in a few slides. Some words about, for the people that are listening, maybe the younger one that maybe know our vision system, maybe not. So let's go very quickly through the system. This is the eye. And we have the idea that the eye is the device that acquires visual perception. In reality, the eye is just the beginning of the perception. So it's the effort I want to ask you is to follow me in this idea of considering the eye only the very first initial part of something that is much more complex. And the idea is that basically the sensation of color and the sensation of everything that is visual takes place in the brain, and you can see the eye as a sort of the brain is curious, so wants to see what's outside itself, and so has this prolongation that goes and sample the world for the brain. So the brain is the chief, the eye is the one that works for the brain. And there's a very, very studied configuration, neural configuration. So from the eye, we go to the brain, and this is a path that we call visual pathway that has a certain characteristic, and we will analyze some of them. A few words about the eye. This is the eye. Those are the cones and rods. The eye is basically is a dark chamber in which that lights enter from, in this case, watching the slide, from the left part, and goes travel all the humor vitrio in order to hit the retina that is back on the right part of the eye. And those are cones and rods that are the sensors that are on the back of the retina. This wonderful picture, you see there's a kind of crowded mass of sensors that are on the retina. Basically, the sensors are of two types. We have cones and rods. Cones are responsible for the vision, daily vision. And so when the amount of light is to a certain level, and then rods start to work on when lights get lower, and so we have lower levels of light. In matter of fact, there's a lot of debate, there's a lot of research also trying to understand how rods interact and works also for the normal vision in daylight. And we did some experiment. We found that there's a kind of interaction between rods and cones in certain conditions, but this is not the topic of this talk. So those are the the guise that gives us the vision, gives us the signal that allow us to orientate ourselves in the world. And some characteristics, the roads, sorry, there's some Italian in the slides, bear with me. Roads are responsible of, bastoncelli in Italian, are responsible for noctura, so we have only one type of roads. And since there's only one type, there's no color. So if there's a common experience to walk in the night with maybe the moonlight shadow and shining, and the things that we cannot perceive any color because the level of light is not enough to activate our cones. And since we have only one roads, no color is attached. That's very important because we need to say that when the light level arrives to a certain degree, cone starts to work, and colors does not come exactly directly from cones, but come from the difference of stimulation of cones. So we have three types. In this case, we have three different types of cones. You can imagine that one is the RGB, a kind of RGB, is not exactly. I will tell you more about that in a few minutes. But basically, the spectrum of light that goes from 380 to 780 roughly is divided in three, and every type of cones is specialized to acquire a certain part of the spectrum. Exactly, those are the three cone spectral sensitivities, A, B, and alpha, beta, and gamma in Greek. Alpha is much lower, not because we are less sensitive to it, but we have fewer cones of the blue. But we will be back into this in very shortly. Some words about the retinal signal. So these are the cone sensitivities that we have a lot of cones that works in our vision system. They acquire the signal. How is this signal? Basically, this is the scheme of the retina, and so we have the cones and the rods that are on the right side. The interesting thing is the light comes from the left side, so the sensors are not faced in order to face the light, but the light hits the sensor from the back. That means that the light has to travel through a series of tissues, of biological organic tissues, and then end up with the cones. The interesting thing also is that we have a series of cells that are very specialized cells. You can see horizontal cells, amacrine cells, bipolar cells, ganglion cells. All these cells works to get the signal from the sensor to the optic nerve. And doing that, if you take a look at the horizontal cells or the amacrine cells as well, there's idea of spatial distribution. That means that every cones is, you can see easily, okay, is connected in some way. Every sensor is connected horizontally to other sensor. This is very important because it makes a sort of initial adjustment of the levels of signal acquired. But there's a lot of studies that is trying to better understand how retina works. And if we are talking about just retinal wiring, there's a lot going on. Because retina is supposed to have many things going on. It's a kind of aggregator of the signal, not just a series of receptors. And to the point that we have 10, you can imagine a kind of 10 different layers, 12 types of ganglion cells. Sorry, NR is missing at the end of ganglia. 27 type of amacrine cells. Is quite recent, the discovering that there's the ganglion cells that are responsible to the connection and activation of the circadian circle. That means that when you wake up, every one of us has a kind of circles that is roughly 24-hour circles that makes you wake up in the morning and fall asleep in the night. And this is linked to the balance of two compounds in the vision, that is the melatonin and the serotonin, and those levels of hormones are in some way are controlled by those cells, and that means that the light hitting the eye and hitting the retina also activate or deactivate, in the sense that, of course, it's a up and down. And so retina is responsible also of this very important working activity of our body. And then going into deep, there's also the idea that is not proven, but there's some works and papers that tells that the idea of having a sort of pick-up zip, kind of compression of the visual information, and it seems that different spatiotemporal representation takes place in the retina. This is because basically we have the need of, we have 100-to-1 ratio between sensor and fibers of the optical nerve. That means that we have much less fibers that goes to the brain than the amount of sensor. And so in the retina, a sort of aggregation of the information is needed and is required. Lateral elevation is the one that I was presenting before, the idea that every sensor is connected horizontally with the neighbors, but also a vertical inhibition seems to take place. That means that the connection is not just, and the propagation of electrical signal is not just horizontal, it's also vertical. And then many other hypotheses like specialization and so on. But this is to tell you that retina is not just a sensor. It's not just a camera sensor, that something that is passive, takes the signal and go back giving signal to something else. It's something more complex. This is the spatial distribution of the signal in the retina. You see the red line indicates the cones, and the blue line indicates the roads. That means that this is a horizontal cut of the retina. That means that basically all the cones are concentrated in the fovea. The fovea is the central part of the retina. That means that if you want to look at the match, football match or a tennis match, you need to move your sight or your head, as you prefer, in order to focus and center what you are interested in, because the resolution, the high resolution, is just in the center. That takes us to another point, that is, does image exist in our brain? From a neural point of view, they do not exist in the retina. That means that human vision is strictly foveal, and we do not have, at a certain, if you take a precise moment in time, you don't have anything that is roughly similar to an image. You have something that is very precise in a small area and very rough in the center. So one of the works of the brain is to aggregate all this information and give us a kind of smooth and detailed representation of the world. That is, it seems simple, but it's not, in the sense that there's a lot of models that try to account for that. But basically, we need to aggregate a lot of information and keep the information stable in time while we watch, for instance, a movie or whatever we are watching at. Just to have your glance of how it works, this is a very old experiment. If you take a look at the point, at the central point, it's very easy to have just stare your gaze in the center, and you perfectly are able to read all the letters. But if you stare, for instance, at the left A, the letter, the big A that is on the left, you lose the chance to read the letters that are near the point. So the gaze is something that accounts very much for our visual perception. But going back to the color, how do we form color sensation? There's two guys, let me introduce. This is Edwin Land. Edwin Land is the founder of Polaroid. He died in the late 80s. And John McCain is very healthy and alive, and Mathieu and Alain know him. And those two guys did an experiment, and the experiment was published in Scientific American in 1959. And they tried to account this idea of how color is really organized in the brain. The experiment was quite simple. There was this, you see, this is on the right part is when we redid the experiment in 2002 at Electronic Imaging. And John is the one with the beige jacket. And the experiment was the following. You have a colored scene, and basically you have a separation of two filters. The red filter, that it's on the left, and the green filter is on the right, as you see from the label of the picture. That means that when you separate an image with two filters, there was pretty common way to acquire color information in those years. Basically, you separate the information, and for instance, something that is red in the image, probably this is a kind of orange or something like that, is very light in the black and white representation. And on the contrary, something that is the opposite, like the red. This is probably a red thing because it's very light. A red apple, I imagine, is very light in the red separation and is very dark in the green separation. This was kind of common. Then the practice is to take those two separation and re-project the separation, so overimposing the separation with the red filter when you acquire the image with the red, and with the green filter when you project the green separated image. But the experiment was not like that. The experiment was simply just remove the green filter. And so if you remove the green filter, what's going to happen? Because from a physical point of view, you have an image that is basically made by red and white. And so you should perceive all the tones that goes from the red, the pink, and the white. But strangely enough, what you perceive is you perceive all the colors. Is a kind of pale color due also to the fact that the separation was a bichromatic separation, but our vision system was perfectly able to perceive all the color. These are images, some of you may recognize Gabriel and Giordano. Maybe. This is exactly the experiment that we redid in 2002. But there's a more interesting experiment as well did by Land and McCann, and the experiment is like that. They took a kind of Mondrian cardboard, and then the Mondrian cardboard had three projectors. The wavelength of the three projectors were very narrow bands, so not overlapping, and they lighted the Mondrian, and then there were three colorimeters that were measuring things, and that choosing patch by patch. Let's start from the pink one. They measure the light coming from the pink patch at each channel, and then they ask to observe what you see, and the observer say, I see pink. And that's very, very common, very normal. But the second part is more interesting because they changed the amount of energy that was lighting the pink patch in order to have equal energy on the three bands. Because basically they were producing a signal coming from the pink patch that was a gray signal. And so this, just to record, when every band gets the same amount of light, basically this is achromatic. But strangely enough, the observer still was seeing pink. And the interesting second part of the experiment was that if you cover everything but the pink patch becomes gray. So the signal is a gray signal, but is perceived as pink in the context. So this to prove that color is not the amount of information, of spectral information that you have in the point, but is the result of the spatial distribution of the information. But we will go back to this very important point later on. And they did that for many patches. I invite you to read the original paper. And for each patch, basically, they were able to let the observer perceive every possible color, or almost every possible color, with the same patch. So a pink patch can become gray, green, and whatever. So what they did essentially was changing the lighting and the surrounding of everything, and then the perception follows and adjust the sensation, the color sensation, according to the spatial configuration. And this spatial things is very important. For instance, here you see there's a lot of what we call visual illusion. We call it illusion, but I want you to think about this name a little bit more in detail. Why those are illusion? Those are exactly what our perception is. So the illusion, we use the terms illusion because they conflict with the model, with the idea that we have about vision. So those are uniform gray stripes. And so since they are uniform, we think that they should be perceived as uniform. But this is our model of vision, is not, of course, if you measure them, they are uniform. But we expect that they look uniform as well, but they do not. And what happens is that every single stripe looks darker on the left and lighter on the right. And this is very important. Basically, what happens is that this principle enhances the edge. And I want you to remember these words, enhance the edge, because this is very important for what we will see in a very short. Another visual illusion, let's keep the term, is the simultaneous contrast. So the idea is that you have 4 gray patches, quite known, and you see this much darker, the one on the left, than the one on the right. But by the way, do you see my cursor, my arrow? Okay, perfect. And so, again, we expect that they should look the same, but they do not look the same. This is pretty right, it has a sense, just to prove that they are the same gray. Again, another simultaneous contrast. The 2 circles are exactly identical in terms of color, but the outer circle looks much bluer because it's surrounded by red, and the inner circle looks much red because it's surrounded by blue. So this idea of contrasting the information from the background is very helpful because it enhances the difference. Enhancing the difference for our vision systems is very important because we need to survive, and so we need to look at things. And the more you see, the better you survive. And so enhancing visual information is a mandatory point for the ecological aspect of vision. And again, look at this illusion again made by Kafka, called Kafka ring, in which we have 3 grays, but they change in very different appearance according to how you move, and more important, if you form an edge or if you do not form an edge. And this is the point. An edge change the sensation. So having or not having an edge, just if you compare the upper left to the upper right, it just this is clearly the same gray, but it becomes 2 different grays just because you form 2 different edges. And this is very, very, very important. So again, edges is the keyword that is repeating in our presentation. Then there's 2 squares, projected squares. Are the same color? Yes, of course. This is the game is having the same things looking different, and so again we have two identical grays that appears very much the same. In this case, it could be interpreted as a more complex things, like you recognize that this square is in the shadow, so should be lighter because it belongs to the series of whites, and this on the outside the shadows should be darker because it belongs to the series of black. In the matter of fact, that it's exactly the same gray, and the point is that here you can interpret as a sensation or a perception. In last time we can go into a little deep, but again, if I go and I consider this as an edge things, it's enough to explain the difference. Here we go. And so why spatial computation? So why our vision is spatial? Why we go into the trouble of organizing vision in a series of spatial comparison and not just grabbing the signal, the color signal from the point. Everyone that working in colorimetry knows that it's so much simpler to consider the color in the point. And in many times we are very happy about that. But vision does not do that. Why? It's very interesting, because here in the second part of the series. So those are the cone spectral sensitivity. Imagine, take a look at this cone spectral sensitivity. One details is that the red peak falls into the green, but this is kind of details. Okay, who cares? You with the red cones, let's call it red cones, you integrate on the right part of the spectrum, so we don't care very much about this. But we should care much more about this. The red, let's call it red and green, should be more correct saying the L and M cones, the long and medium wavelength cones. They are so much overlapped that the way they sample the spectrum is so similar that if you produce an arbitrary spectrum, they sample it in more or less the same way. And the maximum ratio about, the maximum difference about the red and the green is just 2. This means that if we use that, imagine you want to use those 3 curves to synthesize a color. But I'm not saying those 3 curves that goes to the brain and produce our sensation. I'm saying just imagine that you have a camera that take a picture using those 3 sensors. And this is the color that you get, the one in the below. And so those 3 sensors are so, the 2 L and M are so overlapped that basically you don't have any real good color, any saturation. And that's pretty strange in the sense that it comes to the idea that the retinal signal from a color point of view is very bad. We do not have any color in the retina that is even roughly like the color that we experience every day. And just to make the comparison, on the upper part, there's a separation, a color separation made by a film, a color film. And you see the big difference. And so what happened? It happens that in the retinal part, we have a very shrinked color space. So the color are not very good color, are very small and not enough detailed. Then something happened during the pathway, maybe a kind of organization of the retina, who knows, it's a very complex phenomenon. And so in some part of our vision system, the idea of opposite color takes place. But what is more interesting for us is that we end up with a color space that is big color space, that is the everyday color space that we have. And the way our brain, our vision system produce this color starting from a very shrinked color is by spatial computation. And so now spatial computation, and we will see more details, is the way our vision use to pump up the colors, to move from a very pale or less saturated color to the everyday colors that we like. And this computation must be spatial, and we will see why in very short. For free is when you buy a magazine that for free you have something else. Exactly. For free, we have color constancy. So color constancy is something that comes for free using the spatial computation. What about, let's open a very, very short parenthesis. What about colorblind people? Colorblind observers are basically person that for genetic reasons, colorblind are mainly male, is about a little bit less than 10% of the male population, so big number. And they basically have some type of cones that work less or doesn't work. And so they have a retina part that is less responsive to the light. And the point is that we study and modelized the color blindness just considering the retinal part. But we have just seen that the retinal part is only a very, not small, but a very limited percentage of the visual process. And so this is how they see or how we imagine they see. And the point is that if a colorblind, a normal person has a visual pathway that is responsible for the big difference of the signal, it is correct to hypothesize that a colorblind observer is not just the retinal input, it's the retinal input plus something else. And so the colorblind observer are exactly as everyone using spatial computation and spatial comparisons to pump up, to expand, to enhance the color. And so I want you to think about that we need a lot of research about how spatial comparison and spatial color works for colorblind people. In fact, you see Shara bubbles here, Mansell 100 use, and CAD test. In every test, edges are carefully excluded. So they try to avoid edges because, as we have seen, edges are something that cause changes and produce changes in the appearance. So every test, not every test, but the major part of the test avoid edges. And again, keep in mind this idea of edges, and I will show you another interesting point. We did a test. What if we introduce edges? So we took a normal Ishara-like plates without contact, and we enlarged the bubbles, enlarged the circles in order to touch one each other. And what happened is that colorblind had a very big increment, a noticeable increment from around less than 20 to more than 34, 35. The more you have edges, the more you see things. And so consider that every colorblind looks to a world that is plenty of edges. And so also the idea of testing color blindness, avoiding edges, could be maybe something that limits our knowledge about how our vision system can respond to a certain stimuli or not. And the same happens to normal observer as well. In chroma glasses, we are having fun in testing some of those glasses. But if you think, what is the principle of enchroma? The enchroma is just a bandpass dichroic filters that cut this part of the spectrum. And they cut the overlap, the crossing part of the spectrum. Basically, in cutting in this way the spectrum, you basically increase the difference among the different response of the cones. But one cones get only one information. And so basically what you are doing in wearing enchroma glasses, you are just increasing the color contrast. not the color in itself. And so you go into producing a more different spatial variety of colors that will be processed by the spatial configuration of the colorblind person. Then we go to the point. This is the hidden secret of every producer of photographic material knows perfectly well. What is glare? Glare is the fact that each ray of light that crosses a lens goes through a lens linearly, but a teeny tiny amount of energy is spread, is scattered around. And scattering, this light scattering, here the sun is below the sign. When the sun appears, the contrast decrease, and you have a strong decrement of contrast, as you can see. But more in details, basically, the light going through the lens is a teeny tiny fraction of this energy is diffused. And so you end up with something that is not a point, but is a point spread is something that instead of being a point like that, this is an exaggeration, of course, is something like that. This is not avoidable. Every time you have a lens, and so we go back to the title of my talk. Every time we have a lens, we have this problem. And take a look at this example. This is a light in the front. These are two color checker, and this setup from the view from the top is that here's the light. This is the point of view. We have this black cardboard that works as a shield in order to do not allow any possible ray of this light to hit the color checker. And so basically, a question for you. If I switch on the light, does the light coming from the color checker change? I don't know who has the microphone, but who has the microphone has the responsibility to answer me. Mathieu, does it change or not? Okay, so microphone arriving.
Can you hear us? Yes?
Very well.
Good. Okay, so if you eliminate only the white panel?
Yes.
Yeah, so the color of the rest of the room shouldn't change, but I guess it will?
Of course, not. It's like spoiling when you go to the cinema. But of course, but the point is that physically this should not change. But
no,
the point is that
shouldn't change, right? The light does not change.
This light hits the lens of the camera and spread, and you see the spread. You see this halo that is spreading. So the amount of light coming through the color checker is not changing at all, but it's changing the spread of the light. And this spread is just due to the lens, to the point that can be very, very big, very strong. And if you take some numbers, you see that the black line is the acquisition without the light, and the red line is the acquisition with the light. To the point that do you agree that on the left side is a much lower dynamic than on the right side? Correct. So we should say that we have an HDR and high dynamic range on the right and a low dynamic range on the left. Do you agree on that?
Yeah.
But surprisingly enough, what we acquire has a much lower dynamic range when the dynamic range outside is very high, and much higher dynamic range when outside the dynamic range is lower. And so there's a kind of contradiction. I increase the dynamic range of the external light, and I decrease the dynamic range that hits the sensor. And this is the key point of not only HDR, but also our vision, in the sense that apparently in a kind of contradiction, the high dynamic range causes a very low dynamic range on the sensor. And on the opposite, a low dynamic range causes a higher dynamic range on the sensor. And so glare is the essence of the limitation of whatever kind of acquisition and vision as well, because we have a lens in the eye. But we will go to that in a very short. So there's also a very false idea that we need to fight. That is, glare is when I have a highlight. No, glare is every single point of a scene, not just the highlights. Let's make this toy example. If I have something that is 1,000 candela per square meter, whatever, and then it's 10 candela per square meter, and then those are two areas, one near each other, and that's this means that I have a dynamic range of 100, maximum divided by minimum. Okay, I can make the hypothesis of 1% glare. That means that 1% of the range of the energy is spread. And believe me, 1% is a very low number. That means that the 1% of 1,000 is 10, and the 1% of 10 is 0.1. And this 10 spreads from the white to the black, and this 0.1 spreads from the black to the white. Okay? Then it happens that the amount of information that's spread from the black to the white is nothing, because 0.1 divided by 1,000 is negligible. And so the white is not affected at all by the glare arriving from the black, but it exists. We don't need an highlight, we say. But what happens is that the white is disturbing very much the black, because the level of magnitude, the order of magnitude of the spread, or the 1% spread, is exactly the same as the black. And so this is a big problem for the blacks. And so the point is that not just that glare is not just to the coming from the highlights, but if you consider that you have 4, 5, 10 millions of pixels in a camera, that means that consider 1 pixel. Imagine we have 10 millions of pixels. On 1 pixel, I have 9,999,000, so on, glare coming to that pixels. And that means that if you give me 10 cents and you are 10 million people, I end up with 1 million euro. That is quite a lot. And so the amount of glare, the energy that is spread, can be very, very, very high. So the point is not just what's outside, but is if I have a lens, the point is what arrives on the sensor. And once I use the image I acquired and the data I acquired from the sensor, I lost the outside contrast. There's a lot of people that use camera or want to use camera to make colorimetric calibration, but it's too late because light travels the lens and you have no more the information on your image plane. But let's show you how big can be this loss. And so these are for color checker. And this is in the trunk, this is on the beach, this is on the beach a bit far away, and here again in the beach. Okay, so I have 4 pictures with the same exactly reflectance acquired in all the scenes. Now, why I pay 100 euros, maybe more, a piece of cardboard that is color checked? Because someone carefully calibrated each reflectance of each patch. And so I know, and it's wonderful work, by the way, and so I know exactly that the first gray is I go by memory, roughly 80% of the white. And the second, let's say 60% and so on. And so if I acquire that in raw, that means I have a linear acquisition. I would expect that if I have a number, a digit number, a digit value coming from the white, I expect that the value coming from the gray, the first gray, would be 80%, and so on. Okay, please interrupt me if you disagree on anything. And so I can do the ratio between how much I expect to acquire and how much I really acquired. And this is the ratio. And that means that I end up with 300, of course, these are the white. The white is always okay because it's not affected by any glare, but the black arrives to 300% error from compared to the white. That means that I have the black that's 3 times lighter. So consider that if this works in color channels, since some colors are darker in some channels and lighter in other channels, that means this ends up in a color shift, in a big color shift. That means that if I have a lens, I cannot trust what I get. And I'm moving your attention from the pointwise value that you can always arrange and fix it to the contrast values. So I'm talking about ratios between colors in the scene. And if you correct to a color, you destroy the other one, and so on. It's not something that you can do at the same time. At the minimum, that means that picture that honestly looks pretty good, this black is almost 180% lighter than should be. That means that I have a tremendous amount of change of my information. And so that means that I cannot trust what I get, to the point that this is for instance, the shrinks of chromaticity acquiring the color checker on a black background or near the marble. And so I have these shrinks of color just because I changed the background. Or even more surprising, look at this color checker that we hang on the wall, and then we put a tripod, we put the camera on a tripod, and we just move the camera. The color checker was the same place with the same light, same everything, but I just moved the camera. And so that means that here the acquisition has a lot of white pixels that disturbs this black. Here the acquisition has less white pixel disturbing that black, and here less again, to the point that we go back to that later, just because I move the camera, I end up with 50% difference in the black. And so how can I trust the picture? The other point is that we put the color checker backlight in the window, and then we frame and we took a shot of the color checker, carefully avoiding being much more narrow, so carefully avoiding the white. So we just frame in a narrow way in order to have only the color checker in the field. But the light bouncing around to the lens end up with more than 250% error in the black. So all these big differences are there, are measurable, but are not visible. That's another good point, because we don't care very much, because our vision are not affected by that. We have the color sensation is pretty stable, but not because color acquisition is correct, but because our vision system is robust. And so we demonstrate the second part of the title. So why we cannot measure color or spectrum if our device has lens. But our device is also our eye. So let's have a look in what happened in our vision. And so let's close the circle and see what happens in what arrives to the retina. And so we did this experiment. We built up black and white slides. Those are single slides. It's a black and white slide, so you see white, but you should imagine transparent. And if I use a single slice, I end up with a 500 range, roughly. That means that the light going through the white is 500 bigger than the lights shining through the black. The trick is using two slices, one over the other, in order to darkening a little bit the transparent part, but darkening very much the black. So if I superimpose two blacks, I go very down in optical density, to the point that I have almost 1/4 of million ratio. So it's very high dynamic range. How much arrives on the retina? This is the glare spread function by Tom Vandenberg. He did a wonderful work in carefully having this model of spread in our eye, basically, and you will see that the spread change according to the age, according to the color of the skin, and so on. There's many parameters, but basically we did a 25 years old brown Caucasian person, and we compute how much, just to have an average, how much of this outside light arrives to the retina. This is the glare spread function in logarithmic, so it's a much steeper function. So this is the scene. How much arrived to the retina? Just to have you a glimpse or to visualize how big is the shrink, I present this in false color. That is, this is optical density that is a log unit. So if I color this in log in this target, you can easily see that the single slide goes from 0 to 2.7, that is 500. And so the white is the transparent, and this is the maximum, and this pale blue is the middle, that is the darker point. The double density goes down to 5.4. And how much of this arrives to the retina? Here we go. The 500 becomes 100, and the 250,000 becomes 150. It's a tremendous shrink of contrast. I did this experiment myself, and so I can tell you that there's a big difference in appearance between the single slide and the double slide. That means that our vision reconstruct the information. So this is the big shrink. But when we measure also the appearance, and you can perceive much more than what arrives to the retina. But here is the most important point. If I plot the difference in luminance, you can see that there's a steep edges. And I remember that these very tiny squares were very visible. But on the retina, edges are no more edges, are smoothed very much by glare. That means that our vision system has a strong need of reconstructing edges. And this explains exactly, I was underlining the word edges many times in the talk, and this means exactly why we need to consider edges a very important information, and why we need to over-enhance edges, because the edges does not exist anymore on your retina, on our retina. And so, since edges become gradients, we have to rebuild the edges, and in order to have an appearance, if you look at me now, and if you look at the slides, you see edges, and you see edges because your vision system, your brain, the whole vision system is rebuilding and reconstructing the edges that are not arriving as they are on your retina. And this is exactly why we have this over-enhance of the edge, because we need to preserve it. And this exactly explains why edges changes appearance, because spatial computation has to consider edges as a kind of more important information. So roughly 1 million outside, about, more correctly, 250,000 outside, 150 on the retina. but appearance is much bigger. And so this spatial computation has the good things that you can get back the information that is not present in the retina. And this to show, this should be moved when, this is the color in the retina of the muscle space. And this is the color of the muscle space as we know the muscle space. So this spatial computation is moving from that color to that color. So this is the kind of inflating and enhancing visual information. So just to conclude, here's the world. The world arrives through our eyes in a very compressed contrast information. And so we do spatial computation. And spatial computation basically has three main issues. We want to rebuild and reconstruct color. We want to recover the edges, and for free, we end up with color constancy. If you start considering color constancies not as a separation of illuminant and reflectance, that does not happen in our vision system, but something that through spatial computation, if we do a kind of normalization of color, that means that color will be much more stable in our vision. That's it. So why our vision is special? It must be special. It must be special because this is the only way to recover the tremendous loss that happens in our retina, in our vision, in our sensor. Merci. Merci beaucoup.